I would like first to thank the organizers for giving this opportunity. I'm going to talk about pseudo-differential calculus and groupoid. So, first of all, we will see what is a pseudo-differential operator and vector bundle. So, vector bundle is a special case of a groupoid. Then I will define a pseudo-differential operator on a groupoid in general, and to do so, we use a tubular neighborhood construction, which provides us a vector bundle structure on a groupoid. So then we will see what is a pseudo-differential operator. And then I will try to elaborate on a geometric characterization toward these operators with a geometric object which is called the deformation to the normal cone, and it is rather global comparing with tubular neighborhood construction for defining pseudo-differential operator on the universe. So which abbreviated as CNC. And my talk is mostly based on the results of Claire Lebon and Georges Scandallis. And I'm not going to refer to them at the time. So, first of all, what is a groupoid? A groupoid is a groupoid that we have a space of arrows, G, and a space of objects. Those are infinite manifolds. And we can identify objects as arrows in G. With the map from G0 to G, it should be smooth. Then we have a source and range map from G to G0, G to G, smooth submentioned. And the inverse map also should be smooth from G to G. And multiplication from composable elements G is also smooth. And as a consequence, I will be diffeomorphism. G2 is a submanifold because we have submersion condition here. And G0 is an embedded submanifold. So this is a definition of a groupoid. And to every groupoid, we can associate a canonical convolution algebra using complexity or picking the whole measure. And then we can complete this convolution algebra to obtain a C-star algebra of the groupoid. Then there are two examples that I'm going to work with during my talk. The first one is pair groupoid. We have source of elements xy equals y and range of xy equal to x, and we can compose them simply by this formula. Then the convolution algebra is given by the composition of the kernels, and we have the kernel in L2, which gives us Hilbert-Schmidt operator. We can complete it to obtain compact operators. This is a well-known example in literature. Then we have another example. which is a vector bundle. A smooth vector bundle, of course. So we have source equal to range equal to pi, and the multiplication is given by the sum of the vectors in the pi bar. And then I can say that the spectrum of this is E star, so C star of E is equal to C0 of dual of the E, and Schwarz function of E with Fourier transformation is Schwarz and E star and multiplication. So then I can compactify this space to this E star to obtain a unit Gaussian star algebra. And I can put E star into a ball, and by some compactification, and I obtain instead of compactly supported functions, I will obtain also functions that have limit in the sphere direction. So this gives me a short exact sequence. So this is the sphere bundle of the star. And so I know that I have smooth functions here and manifold with boundary. So I take the Fourier transform, Fourier inverse of these functions. And then by Fourier inverse, I obtain the formula of pseudo-differential operator on a vector bundle. So this formula is this is the definition of a pseudo-differential operator on a vector bundle, and this integral is convergent as a multiplier and as a distribution. And as a distribution, we can show that the singular support of this distribution is in the zero section of the vector bundle. So this helps us to define a pseudo-differential operator on the groupoid. To do that, we use tubular neighborhood construction. So
the integral as it stands, it's just a conormal distribution, right? So not so clear yet what the operator is.
So we can apply P as a distribution on F, and then PF will be the integral of A of x psi and F of x psi d psi.
Okay, so the function you wrote down is a symbol then?
Yeah.
Okay.
Exactly. So I have G0 as an embedded submanifold in G, and I can use inverse mapping theorem to define a diffeomorphism from N to V. So what is N? N is the normal bundle of G with respect to G0, and V is the neighborhood of G0 in G. So this is a diffeomorphism And this diffeomorphism has the property that G0 in G looks like the zero section in N, and the differential in the normal direction is identical. So this is the tubular neighborhood. Now I can say that I am provided with a vector bundle structure on G, and then I can have the same story to so it can be written as where this is some smoothing thing, and so this definition is dependent somehow to the choice of this neighborhood V. And if I change this tubular neighborhood, then I get different kappa, such that this sum will be the same at the end. So this is somehow local in some sense. And so we can see that also the adjoint of the operator is not well defined because it is dependent to this theta. Now I want to use another point of view, which is first. So I'm going to define deformation to the normal cone, and an important example of it is tangent groupoid, which was first defined by Alan Cohn. So a tangent groupoid of a manifold M is given by Tm equal to M plus M Tm plus 0. This is a kind of interpolation between points here in the space and nearby points in the tangent space. So the groupoid structure is clear. We have a pair groupoid here. So I have in the first part I have range of x, y, lambda equal to y lambda, sorry, x lambda, and the result of x, y lambda equal to y lambda. And in the second part, I have vector bundle structure, so it is the range of and in the second part, I have a vector bundle. This is equal to the source. Vector psi is a tangent vector is x and 0. Now we can see that it is easily enclosed with the groupoid structure over M cross R. But now I want to put some smooth structure on it to have a Lie groupoid. So to do that, so I know that here I have some open things and here I have some closed things. The point is that how can I glue these two things together? So assume that I'm given a sequence xn, yn, and lambda n, and I want to see what does it mean that it converges to point x psi and 0. So the groupoid structure tells me that xn should tend to x, and yn should tend to x also because the source are equal to x, and lambda n obviously should tend to 0. Now lambda n determines the velocity of this convergence. So I can say that xn minus yn over lambda n converges to psi. And this means that we are multiplying our distances by the parameter lambda. We make the distances bigger and bigger, and then we obtain these tangent things at 0. So this is the smooth structure of tangent groupoid. Now I would like to give an example of it, which is T of Rn. This is isomorphic with Rn cross Rn plus R. This is a good example to see what we are doing here with these Coulombs. So I have the action of Rn on Rn cross R. And so when Rn acts on Rn cross R, I can see that, so I have kind of this action, right? This action is given by psi acts on x and lambda, so when lambda is different from 0, I can see that I have kind of a translation from one point of Rn to another point, and this is a translation which is escaped by a parameter, but still it's a translation. So every 2 points in Rn determine an arrow, so it's a pair groupoid structure. So when lambda is different from 0, I have Rn cross Rn as a pair groupoid, and when lambda is 0, I can see that we are doing nothing over each point of Rn. So we have kind of arrows over each point. So over each point, I have the group, and the group here is Rn. So again, I have a group of Rn indexed by Rn, so it is Rn cross Rn, but this is not, the structure is different. So it's copies of Rn, which gives me a tangent space of Rn. So this is an example for tangent groupoid. Now, this is actually a special case of a more general case. Here we have we have a manifold. So we can define deformation to the normal cone for a submanifold L and the manifold M. We call it DNC of M and L, deforming along this submanifold. Here, the manifold is M cross M, and the submanifold is the diagonal. Now, in the case of the groupoid, you have G0 sitting in G, so we can define the DNC of G and G0. This is defined by G cross R star union N cross 0. So again, it is obviously endowed with the groupoid structure over G0 cross R. And it has also a smooth structure, so it's a Lie groupoid. The smooth structure, for defining the smooth structure, I can use the tubular neighborhood construction again. I show it by big theta. This is a map from N cross R to G and G0. And so this is defined by theta of x, 6, 5, and p belonging to DNC of DNC0. Now, here I define it by the tubular neighborhood isomorphism, theta, but it can even be defined for an immersed submanifold object. So we may not have tubular construction anymore. So here I write it like this, but there are other ways to define smooth structure without using tubular neighborhood construction. So it is really natural, and it doesn't depend to this tubular thing. And unfortunately, I need to.
Does it work for you?
No, I can erase it. It's the good order. So yeah, we put a smooth structure on DNC, so it is the groupoid. And now I can define the Schwarz function on DNC, which will be the Schwarz function on N cross R, extend naturally to compactly supported function on T. So, am I right now? So I have S of 0, which is a Schwarz function on the vector bundle N cross R, plus compactly supported function and then here I have an ideal J in this space, which is defined by, so I have F in S of DNC of G and D0. And I will say F is in J if for every compactly supported function on G, if T is on G, then T can converge to 0, and it has rapid decay. And this is equivalent to say that the function ft, I take a Fourier transform of ft to obtain a function. Ft hat is infinite flat on G0 constraint. So this is the definition of T. And
what is it, Sophie?
F that we define here is a family of densities. Because this is families of groupoid indexed by R, actually. It's a groupoid over 0 cross R. It's a family of groupoid over R. So this is J, and there is a geometric characterization of pseudo-differential operator given by Deformation and Georges Candelis that every 0 order pseudo-differential operator can be written as integral from 0 to infinity of ft dt over t. Now, if I add the power of t, I will obtain other order pseudo-differential operator. So the n order pseudo-differential operator is ft dt over t to the power n plus 1. And this integral has some advantages that it doesn't depend to the pixels of the neighborhood. And if I have ft positive, I will obtain a positive integral. And we want to see what does this characterization satisfy, or what we expect from composition of two operators. I assume P is a m order pseudo-differential operator, so it means that I can write the integral of. So I forgot to say that F here is in J. Actually, F is in J. This is u over u to the power n plus 1, and then I have u, which is integral of gs s to the power n plus 1. So this is a m order pseudo-differential operator. This is a pseudo-differential operator of order m, and pq is integral of the U star ds U ds s to the power n. And I can say that so we can change the U and S. We can change the variables to take this integral over 0, 1 ft theta is g1 minus theta t. Theta to the power 1 plus m. 1 minus theta to the power 1 plus m. C theta. And dt over 2 to the power n plus 1. So here I obtain we can show that this parenthesis is infinite flat on G0 cross 0, so it means that the Fourier transform of this integral is infinite flat on G0 cross 0, so it means that this belongs to J. And I obtain an integral of something in J, dt over t to the power n plus 1, which means that it is a pseudo-differential operator of order n plus n. And this shows that this definition satisfies what we expect from the usual pseudo-differential operator definition that we know. I'm going to stop here. Thank you so much.